All right, recording is rolling. Welcome to Wednesday, September 27th. So we're doing two Kahoots today, two Kahoots. If you want to follow along with a printed version of the questions, you guys remember a long time back, I gave you guys this packet with these 6 slides on the back, right? So first page is Newton's first law, which we did already, right? And then today we're going to do Newton's second law questions and Newton's third law questions. So if you want to follow along there, a bunch of you guys are already, as you guys have your laptops out, a bunch of you guys are already logged on before I hit record, so that is awesome. You guys remember here, Newton's second law of motion tells you how things accelerate. There's some net force acting on some mass, right? And Newton's third law is the equal and opposite rule. So you have two different objects interacting, right? And then the force between them is always equal and opposite. All right. You guys remember your textbook puzzles are due this Friday. We did cover all of them in class, so some of you guys may have already finished them. I know some of you did because some of you guys already turned this in, right? But if you want an extra day or two, you guys got that. You guys have a take-home quiz that I gave you guys yesterday. Does anybody need that take-home quiz? Anybody not get it yesterday? Take-home quiz, right? So due Friday, right, for forces, dynamics, and then projectile quiz. I haven't handed this back yet because I'm still waiting on like 5 or 6 students in. Guys, double check, focus, make sure you personally have turned in, because if I don't get this would be super late by now, right? So if it's not in by Friday, I'm just gonna have to put it in 0 so I can get everybody their quizzes back. All right, let's switch over to Kahoot. Oh, look at you guys go. All right, you guys are all ready. All right, that's good. All right, and let's go. All right, so Newton's second law, we're starting with. Second law of motion. Acceleration produced by a net force is yeah, there you go. Yeah, all the above. Right. So I flip my screen over and just point that out. Okay. So acceleration is in the same direction as the net force, right? That's a vector and a vector right there. Mass is a scalar, right? But vector, same direction, right? It's directly proportional to the net force. Acceleration is, right? If you triple the net force, you triple the acceleration. Acceleration is inversely proportional to the mass. The greater the mass, the less the acceleration. There you go. There's all 3 parts right there. Points on the board. When an object reaches terminal velocity, so it's falling through the air. It's falling through the air. There's some air drag. What is its acceleration? Yeah, 0 meters per second squared for terminal velocity. You're dropping an object off a cliff, it'll start falling at about 9.8 meters per second squared. But when it hits that air drag, that tapers off. Here, let's here, gonna flip my screen and show you guys some drag force going on. Okay, so suppose you drop an object. Now, if it's in a vacuum or if it's been falling for just like half a second, maybe something like this, right? Now let's include air drag. Right? So the drag starts to build up. That drag force, in fact, is proportional to the speed squared. So the faster it's falling, the more the drag builds up until eventually it reaches this condition right here, which would be equilibrium, which is like terminal velocity. This is what V versus T looks like. So it starts off falling at the rate of gravity, but then eventually it goes to constant velocity would be 0 acceleration. I guess the slope of that graph would tell you something about acceleration. All right, we got Blakey, Zane, Patrick, Blakey again, and Kylie. Book weighs 4 newtons. When held at rest in your hands, what's the net force? Held at rest. 0 newtons. So if you do a free body diagram on the book, it'd be 4 newtons down for its weight, but also collectively 4 newtons up for the force from your hands. So the net force is 0. Guys, anything at rest, what's the net force always? 0 newtons. Right? For that matter, anything at constant velocity, what is the net force always? Also 0, right? Because at rest or constant velocity are both equilibrium, right? So yeah, the answer to that's always going to be 0 newtons. All right, I got Andres, Kylie, Zane, Patrick, and Blakey on fire at the top. Girl pulls 10-kilogram wagon with 20 Newton force. Let's say she's pulling horizontally. What is the acceleration? Acceleration. Yeah, 2 meters per second squared. Here, I'll flip over and point that out. Okay. So this is just real simple application of Newton's second law of motion. Oh, here, let's save us a minute with notes from last class. Suppose this is your wagon. The wagon might have a weight and a normal force, but those are just balanced out as long as the sidewalk's just horizontal. Right? She's pulling horizontally with 20 newtons. Okay? So say the mass of the wagon was like 10 kilograms. Okay, so I got 20 newtons acting on 10 kilograms. That divides out to 2 meters per second squared. So now this wagon is accelerating at 2 meters per second squared. If it started at rest, then I could say it's like speeding up. It's gaining 2 meters per second every passing second. That's where it's coming from. All right. A little leader shuffle right there. Rock is thrown vertically into the air. At the very top of its trajectory, what is the net force on it? Yeah, it would just be its weight, right? Now, if it's in a vacuum or air drag is negligible, then the entire time it's in the air, the answer is always its weight. If you include the air drag, then the net force changes on the way up and on the way down. But at the top, it would still be equal to its weight. The net force would be, because there would be 0 air drag because 0 speed. Right? You guys remember air drag is proportional to the speed squared. All right. Zane on fire, Blakey in the lead. Suppose a particle is accelerated through space by a constant 10 Newton force. Suddenly, the particle encounters a second force of 10 newtons in the opposite direction of the first force. What does that particle do? One winner. One winner. I wonder who got that. Ooh, well, okay, let's look at the explanation first and we'll find out. All right. So now we're out in deep space. So whatever the applied force is, I guess it's the only force, right? Hey, maybe this could possibly be a rocket, maybe? I don't know. Or they said a particle, but if you want to attach a different story to it, right? So we got this particle, 10 newtons, which means it's speeding up. Right? It's going faster, faster, faster. Right? Then suddenly, pow, another 10 Newton force appears, exactly opposite of the first one. Guys, now what is the net force on that object? 0. The sum of the forces is now 0 newtons. Guys, 0 Newton net force. Is that equilibrium? Does that mean the object stops? Or does that mean it just no longer accelerates? Now we're back to Newton's first law of motion, aren't we? Right? So law of inertia. So if it was at rest, it'd stay at rest. But if it's in motion, it's just going to continue with whatever velocity it had at that point. Right? So now it's constant velocity. So the answer is constant velocity. Yeah. I think on that one. Constant velocity now. Okay. Who got them points? Oh, wait. Anybody there? It's mystery. Pressure is defined as, you guys remember a bed of nails? Just remember the longest straw you can use on Earth's atmosphere? Pressure. It's pressure. Yeah, force per unit area. There you go, force per unit area. Hey, what were some units for pressure? We went over several different units for pressure. What's one way you can quantify pressure? do you guys remember PSI? It's like pounds per square inch, right? Now we don't use that so much in this class, but maybe if you go buy a bike pump, right? In this class, we tend to use what? Like Newton per square meter is sort of analogous to pounds per square inch, Newton per square meter. But there's a name for that. I think it's the next question though. Right. I guess Sophia got the last question, must have, because streak of 4. There you go. All right. There's also atmospheres. You can quantify pressure in atmospheres. Right? The unit for pressure. Unit for pressure. There you go. Newton per square meter, also called pascals, right? We'll tend to use in this class. But there are many correct answers, right? Pounds per square inch works, atmospheres works. If you follow the weather, maybe see like bars or millibars. You can even do like heights of fluids, like millimeters of mercury is a common way to do it, or like meters of water. I got Sophia on fire, Andres, Kylie, Zane, and Blakey. Tennis ball, solid steel ball with the same diameter are dropped at the same time. Which one has a greater force factor? Yeah, the steel ball. The steel ball. Here. So let's get these two. Here's the tennis ball. Here's the steel ball. Okay. All right, we're drop them both. Okay. Here is the free body diagram for the tennis ball. Right as we're releasing it. It's got some weight. Right, that's it. Okay. Here's the free body diagram for the steel ball. Ooh, it's got a lot more weight. That's it. Okay. So therefore a greater net force. Okay. I think the next question also involves these two balls. Let's see. Tennis ball, steel ball, same diameter, dropped at the same time. In the absence of air resistance, who has the greater acceleration? Yeah, same acceleration. That's a classic question that keeps coming back over and over. That's the Galileo story, right? Galileo runs up the Leaning Tower, drops off different objects. They fall side by side all the way down. Right? Even though the steel ball has a greater weight, it also has a greater mass. Right? This is tennis ball, this is steel ball, right? So that the two effects cancel out. You guys remember the story? Two kids on the island, they want the Hershey's bar with the almonds in it. You guys remember that? They're trying to figure out which one hits the ground first, right? And they come up with different ideas, but you put their ideas together, you get Newton's second law of motion, right? You get greater weight acting on a greater mass gives you the same acceleration type, right? Now, I should have included for the next question here. I'm just gonna ask what I should have asked for the next question. What if you include air drag now? So now these balls are falling through the air. They're falling through the air. Let's say sometime later they're like there and there. Let's get a tennis ball, steel ball. It's all shiny. Right. Falling through the air. Right. Now do they hit the ground at the same time? Falling through the air. No, in a vacuum they definitely hit at the same time. But through the air, right? Let's say the air drag builds up significantly. You guys remember air drag is proportional to the speed squared. Right? You guys remember that? There's a bigger equation. It's on that poster over there on the wall, but it's proportional to the speed squared. Suppose they've been falling for like 1 second, and I'm gonna make them like pick up speed at the same rate. Let's do a check-in on them. So their weight didn't change. Here's the weight for the tennis ball. Here's the weight for the steel ball. That's the same as before, right? Right? If it was through a vacuum, that would be the end of the story. But through the air, if they pick up speed at the same rate, then they would have the same drag force because drag force is also proportional to the cross-sectional area, but that's the same for both, right? Right. So suppose you have a drag force that builds up looks like this about, right? So they got the same type drag force because they're same speed, same size, right? Ooh, now compare these two balls, guys. Are they both still accelerating? The steel ball is because there's a net force. Is the tennis ball still accelerating? No, it has zero net force on it. So the test ball has reached terminal velocity. It's going to go down at constant velocity. The steel ball is still picking up speed. So who's going to win the race to the ground now with air drag? Steel ball, right? Only if you include air drag, right? That should have been the next Kahoot question, but anyway, just asked it there. Let's get a 21st question. Pull horizontally on a desk with 150 newtons and it doesn't move. The friction force must have been 150 newtons. Now you're pulling with 250 newtons and the desk slides at constant velocity. What is the friction force? Constant velocity. All right, let's take a look at these two free body diagrams where the desk was, here's the desk. It looks like a block, I guess, right? See you drop, right? Right. Versus when it was sliding at constant velocity, right? So starting out, the desk has a weight and a normal force, and those just balance out, whatever, right? We're pulling this desk with 100, or did they say push, pull? I don't know. There's some applied force, 100 newtons. So the friction force must have also been 100 newtons. Now this is static friction, right? That's kind of like if you have an object between, say, the surface of the object and the surface of the paper, right? If I push with a little force, there's a small backwards friction force. If I push with a medium force, there's a medium friction, right? So the friction force will always automatically respond to the applied force to keep it at rest, right? Now, once it's in motion, it's a different kind of friction because it's kinetic friction, right? So probably a smaller coefficient of friction, right? But the key here was they said constant velocity. Guys, what do you know about constant velocity? What's the sum of the forces? Zero, because that's also equilibrium. Isn't constant velocity equilibrium? Isn't constant velocity still zero acceleration, which means zero net force, right? So even though you're applying 250 newtons, the friction force is still matching that. I mean, it's kinetic friction rather than static friction, right? But the answer is 250 newtons. That's the answer. There's your free body diagram for that desk right there. Right. 250 newtons is the friction force. Let's see how you guys did. Oh, that was a tricky question. But you know now. Now you know. When the angle of incline with the block resting on it increases, what happens to the normal force? I'm gonna cut this off at the 30-second mark. You guys get 10 more seconds. All right, well, here, let's switch this over. All right, here's the answer right here. Here's the answer. All right, so here's your block on a surface. Now we're going to see that angle of incline increasing, right? What's happening to the normal force? It's getting smaller until you have a vertical wall. Put a block against a vertical wall and let it go. Well, no, there's going to be no normal force. It's going to approach zero. It's a cosine relationship. Cosine of 90 degrees is zero. So the closer your angle gets to 90 degrees, the closer that normal force is also going to get to zero. Hey, all right. All right. I got Kylie, Sophia, Andres, Zane, Blakey. Speeding truck locks its brakes and skids to a stop. What if the truck's mass had been doubled? Now what would happen to its skidding distance? 10 more seconds. Three, two, one. So, right. So there's a post over here that addresses that question. Well, sort of. It's like the next step. Right. So here's a car going some initial velocity, and it brakes to a stop. Right. Free body diagram. It's got a weight. It's got normal force. Those two are balanced out. Right. And the friction force is acting as the net force that lets it slow down. Let's do second law of motion. Second law of motion. F equals ma. In this case, the net force is provided by what force? The friction force, right? Because the two verticals cancel out. The horizontal friction force is the net force, right? But do you guys remember friction force is coefficient of friction times the normal force? These two guys are related, right? There's some material property between these tires and this road. If it was an icy road or a wet road or a dry road, that is taken care of by this coefficient of friction. Okay. So multiply that by the normal force and you get the friction force, right? So we made a little substitution right there, right? Oh, but the normal force, what is that equivalent to? The weight, which is mg. And at this point, guys, what cancels out on both sides? The mass of the car. So the rate the car can slow down, that's what acceleration is in this context, right? The rate the car can slow down has to do with two things, and only two things. The coefficient of friction between the tires and the road, and the gravity field of the planet, but nothing to do with the car's mass. So if you go load up the car with a bunch of groceries, yeah, makes no difference to the rate the car can slow down. Now, the actual question was, what happens to the braking distance? But if you start with the same initial speed, initial velocity, and you slow down at the same rate, then you will also have the same braking distance. The answer is the same braking distance. Let's see how you guys did. Yeah, all right. Same braking distance. Nice. All right, points. If the force acting on a cart doubles, what happens to the cart's acceleration? Yeah, what? Oh, okay. Oh, somebody got it. Force doubles, the acceleration doubles. Here, let's take a look at that. Yes. So you have a car, you double the force, they're gonna double the acceleration. Because what if you have 1 Newton acting on 1 kilogram? Is that 1 meter per second squared? What if you double the force to 2 Newtons? 2 Newtons on 1 kilogram. Now we're up to 2 meters per second squared. Right? Double the force, double the acceleration. Um, well, look, what says doubles, right? Doubles the force. Yeah, the force doubles, the acceleration doubles. Well, that would be zeroing out the force. That's all right. Oh, how about no? All right, Zane on fire, top spot. Suppose a cart's being moved by a force. Suddenly, a load is dumped into the cart, so that the cart's mass doubles. What happens to the cart's acceleration now? Ooh. Half the acceleration. Let's see why half the acceleration. Right. So can you guys imagine you're in Publix, you got your grocery cart, you're pushing with some force, right? And you're going down the aisle, and you're just like dumping a bunch of groceries, and I'm like, all right, give me all the food, like get cut off the shelves. Right? So if you're pushing with a constant force and that mass is increasing, wouldn't the acceleration be decreasing? Right? Right? Let's put some numbers in here. What if it was 1 over 1 is equal to 1? Right? What if it was 1 over 2? Now it's like a half. Double the mass, get half the acceleration. Frozen pond, ice starts to crack. You lie down on the ice and begin to crawl. What's that going to do physically? Yeah, decrease the pressure. You guys got that. You guys ever seen snowshoes? Snowshoes? Suppose you're up in Alaska and there's some really deep snow. It's like 5 feet deep. You want to walk across it. Hey, put on these skateboarded looking shoes because it'll take your weight, which doesn't change, and it'll distribute it over a larger area. Yeah, now you can plop, 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 walk across the snow. All right, Zane, on fire. Top spot. 20 Newton falling object encounters 4 newtons of air resistance. What's the net force? Yeah, 16 newtons. Right, 20 down, 4 up. The difference is 16 newtons. Hey, I got a follow-up question. Guys, what's the mass of this falling object? What's the mass? Is it 2 kilograms? 2 kilograms, right? What is the acceleration at that point of that object? What is a 16 Newton net force acting on 2 kilograms? What's 16 divided by 2? 8. 8 meters per second squared. Ooh, which is a little bit less than the full free fall rate, right? Makes sense, right? I think it's one of your quiz questions is about like that. Maybe 2 of your quiz questions. You pull horizontally on a 50 kilogram crate with 350 newtons. The friction force is 200 newtons. What's the acceleration of that crate? All right, nice, nice. All right, you guys all got that? Just for the video, if somebody's watching this video and isn't sure where that comes from, there we go. Here's the setup. 50 kilogram crate. 50 kilograms is the mass, right? Which means it weighs 500 newtons. The normal force is 500 newtons if it's just on a, say, a flat surface, right? So that's pretty good. Right. We're pushing this thing with 350 newtons, and there's a resistive force of 200 newtons. So I'll say acceleration is net force on the mass. The net force is 350 newtons in the direction of push minus 200 newtons resisting that. Right? It's acting on 50 kilograms. Right? That looks like 150 newtons on 50 kilograms. That's 3 meters per second squared. All right, nice job. You guys got that. Sophia, on fire. Andres, Kylie, Blakey, Zane. Jumbo jet cruises at constant velocity. The thrust from its engines is 50,000 newtons. How much air drag on that jet? Yeah, 50,000 newtons. Here, show you guys real fast because this poster's been waiting. This poster's moment of glory right here. It's been waiting for this question. So thrust force, drag force, if they're balanced out, that would be a constant velocity scenario. Constant velocity is equilibrium. Equilibrium. All right, and you guys figured that out. Oh yeah. Okay, imports. Right? It's because equilibrium. There better be a 0 net force, right? 0 Newton net force. There's constant velocity. All right. For the win! For the win! 20 Newton falling object encounters 20 newtons of air resistance. What is the net force on the object? 0 newtons, right? Hey, would that be a case of terminal velocity? Like whatever speed it's going, it's just going to go to, maybe it's a parachute, right? It's just constant speed all the way down. All right, to the podium. with the bronze. Kylie with the silver. Blakey with the gold. Zane. Runners up. Andres and Sophia. Right, nice. Right, let's do Newton's third law. Newton's third law. All right, recording resumed. All right, we're about to start Newton's third law. Newton's third law. All right, you're about to hop in. That pin should show up at the bottom of the screen. Here we go. This is the equal and opposite forces rule, right? You have two different objects interacting. Right? Forces are always equal and opposite. Let's see. First question. Whenever an object exerts a force on another object, the second object exerts a force of the same magnitude, opposite direction on the first object. Is that always true? Sometimes true? What is that? Always true. That is Newton's third law, right? Newton's third law spelled out. Is always true. Always true. All right, Blake, the top spot. High school student hits a nail with a hammer. During this collision, there is a force. Yeah, on both the nail and the hammer, right? Hey guys, which force is bigger? The force on the nail or the force on the hammer? For every force, there's an equal. They're equal. Same force. Same force. Same force. But that hammer's a lot more massive than that nail. Ooh, right? Same force. Same force. Archer shoots an arrow. Consider the action force to be the bowstring gives the arrow. What's the reaction force? Bowstring pushes arrow. What's the reaction? The arrow against the bowstring. Action reaction. Bowstring pushes arrow. Arrow pushes bowstring. Zane, Patrick, Sophia on fire. Andres, wait. Player catches the ball. Consider the action force to be the ball against the glove. What's the reaction force? The ball hits the glove back against the ball. Yeah. Now, some of those other forces might also be at play in a larger system. But yeah, the immediate action reaction is ball hits glove slows down the ball. Action reaction. All right, Andres on fire, top spot. Player hits a ball with a bat. Say the action force is the bat against the ball. What's the reaction force? So the bat hits the ball. What's the reaction? The ball against the bat. But guys, which force is bigger? The force on the ball or the force on the bat? They're the same. They're the same. Same force. Same force. Right. Same force. Right. As the ball falls, the action force is the Earth's mass pulling on the ball. What's the reaction force? The Earth pulls down on the ball. What's the reaction? Yeah, the ball pulls up on the Earth. Earth pulls down on the ball pulls up on the Earth. Action, reaction. There we go. All right, Sophie on fire, Patrick to the top spot. Unfortunate bug against the windshield of the moving car. Compared to the force of the car on the bug, force of the bug on the car is what? The same force. But it's a small force. Well, at least from the point of view of the car, right? The same force. Same scenario. Compared to the change in motion of the car, the change in motion of the bug is what? change in motion. Yeah, is much greater from the bug's point of view, right? Here, this actually is a crossover back to Newton's second law of motion. I know all these questions are somewhat related to Newton's third law of motion. That's the theme of this particular Kahoot, right? But we're gonna have to look back at Newton's second law of motion. Now, both the bug and the car get the same force on them during that interaction, same force, same magnitude force, opposite directions, right? But the mass of the car is huge. So, guys, if you're driving on the road and you go against the bug, does your car slow down? Yeah, a tiny bit, right? It's like imperceptible, right? But a tiny, car a little bit, right? But from the bug's point of view, the same force acting on a tiny, like 1 gram bug, ooh, I bet it's a huge change in motion for the bug, right? Right? So same force, different masses, different accelerations. Hey, what if you were driving your car through like a million bugs, just like bug slaughter? Right? Now do you think your car would maybe significantly slow down? Maybe so, right? That mass was big enough. All right, back to third law. All right, got Andre, Zane, Sophia, Blake, Patrick on fire. Horse pulls the wagon at rest. The wagon pulls back on the horse. Can the wagon even be set into motion? Yeah, of course it can be set in motion. You guys have seen the wagon be set in motion, right? Now, what's the deal with this? Right. So yeah, here's Paul here text, but he's got like a whole cartoon answer to this, right? The horse pulling the wagon. Right. Now, the tension force and the ropes connecting the two, yeah, the tension pulls back on the horse as much as the tension pulls forward on the wagon. Right. So how can this system move? Well, because the horse gets to dig his hoofs into the ground, and now there's like a pushing force against the ground, maybe like a friction force, versus the wagon has this wheel, so it's just going to roll. So there's an external force from the ground on the horse hooves that allows for the motion of that whole horse cart system, right? But yeah, the tension connecting the horse and the wagon is the same both ways, right? But yeah, get that into motion. All right, Sophie moving up. Patrick still in first. Large truck, small car, traveling the same speed, have a head-on collision. The vehicle to undergo a greater change in velocity. Is the small car. Guys, which vehicle has the greater force on it due to the collision? Greater force. Same force, right? But same force on the small car will change the motion of the small car a lot more. You'd say accelerate the small car a lot more, right? The large truck, the large mass doesn't change its motion nearly as much. If you had to be in that collision, which vehicle would you be safer in? The large truck or the small car? You'd be safer in the large truck, right? Because your motion wouldn't change as much. So maybe the force on you personally wouldn't also be as much, right? But the force interaction between the car and the truck is the same both ways. All right, Patrick on fire, still in the lead. According to Newton's third law, if you push gently on something, it will push gently on you. Action reaction, equal and opposite. There you go. Patrick's got every single question right so far. Earth pulls on the moon. Moon pulls on Earth. This is evidence that what? Yeah, they're pulling on each other for an action-reaction pair. There you go. So the red and the blue are true. So yellow, both of the above. Pulling on each other, action-reaction. There you go. Nellie Newton holds an apple in her hand. If the action force is Earth pulling down on the apple, what's the reaction force? Earth pulls down on the apple. What's the reaction? Is it the apple pulling up on the entire Earth? I think it's the apple pulls up on the earth, right? Which was not actually one of the listed ones here. I'll check. Now these other forces are also actually they're both talking about the normal force, which might be equivalent to the weight, but it's not equivalent because of Newton's third law, right? It's equivalent because of equilibrium. Yeah. So the earth pulls down on the apple pulls up on the earth. That's your action reaction pair right there. Bronco the skydiver falls toward earth. The attraction of earth on Bronco pulls him down. What's the reaction? So the earth pulls down on Bronco. What's the reaction for? Yeah, Bronco pulls up on the earth. Right. I should have had a multiple choice option that said something about air drag, which also would have been incorrect. Right. Yeah, Bronco pulls up on the earth. Earth pulls down on Bronco. Bronco pulls up on the earth. Action, reaction. Force exerted on the tires of a car to accelerate the car on the road. The force is exerted by how does your car move? What is the external force that's allowing your car to be put into motion? Yes. Yeah, the friction from the road. Right? Guys, if you were on an icy road, would it be really hard to get the car going? And for that matter, once it is going, it's hard to stop it too. Right? Yeah, you need the friction from the road. The road is actually pushing the car that's allowing it to change its motion. Okay. External force from the road. So friction force. Rocket is able to accelerate in the vacuum of space when it fires its engines. The force that propels the rocket is yeah, right. So those are equal and opposite forces there. The red and the blue are equal and opposite. The rocket pushes on the exhaust gases. The exhaust gases in turn push the rocket forward. Yeah. Karate chop delivers 1900 newtons to a board that breaks. The force that acts on the hand during this feat is 1900 newtons. Equal and opposite forces. Force pair. Zane on fire, moving up. Got Andres Patrick in the lead. If you weigh 450 newtons, sit on the floor. You exert a force on the floor of, because it's not accelerating. Yeah, 450 newtons. As long as you're not like in an elevator accelerating, right? Just at rest. All right. Weigh 450 newtons, sit on the floor. The floor exerts a force back on her of also 450 newtons. So that'd be like the normal force there, right? Okay. So normal force, normal force. For the win, for the win. Two people, tug of war. Each person pulls with 600 newtons force. What is the tension in the rope? Here's a hint. Whether it's a person on one end and a tree on the other end, or say a person and an elephant, or a person and a person, those are all physically equivalent scenarios. Yeah, the answer is just 600 newtons, right? If each person's pull is 600 newtons, the tension in the rope is also 600 newtons. Yeah, yeah. Back to the podium with the bronze, Zane with the silver, Andres, and the gold. Oh, Andres. Yeah, and lady. Nice job, guys. Nice job. Oh yeah. Everybody winning.